Hi everyone, we are from Group 2 Semiconductor Device and my name is Mohammad Ali ibn Shahadat. My metric number is 191391 and my topic is work function.
And I'm Mohammad Sahal Hassan. My metric number is 191488. And today I'll talk about flat band voltage.
Okay, my name is Mazin Hamza. My metric number is 191287. My topic is essential voltage.
Hi, as my part is work function, now I will give the definition first. Work function is like, if you think about in solid state of physics, the maximum thermodynamic work needed to remove an electron from a solid to a point in the vacuum immediately outside the solid is called work function. Here the immediately is very important. Now I will say what is this. Immediately means the electron position is far from the surface on the atomic scale. Now I will go to the further explanation for work function. I will start by giving a formula which is W is equal to E phi minus EF. This is Fermi energy, we all know that. And this is charge electron. And this is electrostatic potential. Electrostatic potential. Now, in this point, I need to show some methods. So I will show some methods for work function. These are some vital methods for work function. So methods like thermionic emission, cold electron collector, then photo emission, and the last important one is Kelvin probe method. So I will write that thermionic emission, দুই cold electron method, then photo emission, and the last one is Kelvin probe. So work function has a very deep impact in semiconductor. So here is surface. Here I want to explain the surface dipole. The work function is not simply the internal, like how to say, it's depend on many things like vacuum level and inside the material, because the formation of an atomic scale electric double layer at the surface. The surface electric dipole gives a jump in the electrostatic potential between the material and the vacuum. So now coming to the doping and electric field effect on semiconductor. So in semiconductor, it's very sensitive, like doping level at the surface and semiconductor, it also controlled by electric field. The sensitive to the electric field in the vacuum. I can show a formula again that can explain more clearly. W is equal to EA plus AC minus EF. So this is very important term which is called electric affinity. Electric affinity. Then EC is the surface. After that I will show a diagram that will explain it clearly. Surface. I will draw a diagram that will explain what is the work function exactly. So this is E here we know that it is Fermi energy. This is EV. So after that we will draw the this whole thing is semiconductor, and this side is vacuum because it's related to vacuum mode. So this is EVC, means vacuum, and this is EC, which is this is EA. So now what is work? You can see that from this point to this point in the semiconductor, this is work. I think this all for me.
So now I'll talk about my part, that is flat band voltage. So let me get started with the definition of flat band voltage. This is applied voltage such that there is no band bending in the semiconductor. As a result, the zero space charge in the region. So now let me explain the whole things. If there is no charge present into the oxide or at the oxide semiconductor interface, therefore the flat band voltage will be equals to the difference between the gate metal work function phi m. This is gate metal phi. We explain like this: phi m. This is gate metal work function, and the semiconductor work function. The difference between gate metal work function and the semiconductor work function phi s is equal to the flat band voltage is Vg. So let me draw the things very very clearly. Let me give you a picture of this. So this is our metal. So this is our oxide. So we take like silicon oxide, and this is our p-type semiconductor, p silicon. So p-type semiconductor. So let me draw the Fermi level first. So E Fermi. This is the vacuum level of metal, and here it will increase. This is called. Let me draw first, then I will explain. This is for silicon. So this is EC. This is called the, as I say, phi m work function for metal, and this whole things is called the work function for semiconductor. So as you see, it's not the same. Like this is here is smaller, here is bigger. So okay, let me. This is EV here, EV, and it will be a little bit up. EV, and EC will be EC. So vacuum level of metal and the semiconductor, as you see, it's not the same. So this difference, we need to give some charge, the voltage. We need to give some voltage to get the equation very clearly. So the equation, as I in the first I told, the equation is so Vg. We explain Vg, but our V FB flat band is equal the difference between metal phi m minus phi s. Yes, phi m minus, oh this is phi s, sorry, phi s. So that's our equation, but still we don't but exactly okay. So I think we get the idea, whole idea. So let me write one equation. Still like this equation, VFB equal to phi m minus phi s is okay. We get the idea, but the exact electron from the Fermi energy to the vacuum level is not the exact same as this like the metal in vacuum. So we need to, how to say this, we need to think a little bit more. Like we have another good equation to solve this problem, not problem, the good equation to exact, like correct. So it will be, the exact thing is V FB is equal to pi ms minus qi over C oxide minus 1 over E epsilon naught OX summation of 0 tox rho ox over x dx. So that's our real equation to get the exact flat band voltage. So I think you get the whole idea, and thanks.
Okay, now, like I said in the beginning, I want to talk about differential voltage, and now is the definition of differential voltage, or FET, is a minimum gate to resource voltage VGS that is needs to create a conditional path between the source and drain terminals, and the full context of the basic usage is important. For example, in control system engineering. And now the base formula is Vt equal Vt MOS plus VFB. Ft MOS is the ideal threshold voltage. So that means no work function differences between the gate and substrate materials, and VFB is the flat band voltage. Vt MOS is the positive for N MOS and negative for B MOS. Now I'm going to give you a little bit of explanation or calculation for this one. Now we start with the terms. The terms, we have 6 terms. The terms 1 and 2 is M, which is doping density. Doping is M. For number 1 is ND. Second one is N. The first one ND is polysilicon gate. Okay, this is for number 1 ND. And for number 2 N, it will be NS, NMOS, or BMOS. For NMOS is NA. And for BMOS is ND over substrate. Okay. For this one we say it's a silicon gate for ND, and this one NMOS and BMOS, and NA is substrate too. So okay. Now number 3. Number 3 is TOX, which is thickness, sorry. Now number 4 is work function, GC, work function, which is work function differences between what? Between the gate and channel. Okay, this is for number 4. Number 5, it's Q. Actually 4, 5 and 6 is Q. What it will differentiate that we will say QDO and QOX. Sorry. And the Q is its charge density. N we said is doping for N. Now we are talking about Q. Q is charging. N for all N. N1 and 2. And charging for Q and Q. 5 and 6. And QDO is depletion region. And the last one is QOX, which is fixed positive. Okay, thank you very much. This is my part.